So in nature, you're seeing this green jellyfish, even though the pure bioluminescent reaction is blue. So this is the collision between my two fields here, between bioluminescence and biofluorescence. And here is the three individuals that won the Nobel Prize for this. So there is Shimomura, who you were looking at collecting the jellyfish. This is Marty Chalpy, who's just uptown, who was able to take the DNA of that fluorescent protein and put it into his model organism, which is a transparent worm. And this is Roger Chen, who then really made a few point mutations to this protein and souped it up like a race car, so it had more applications. I'm not going to get into the applications right now, but we'll talk about that towards the end. But just a little bit of how this seemingly simple finding of this jellyfish giving off blue light and another compound converting it to green has turned out to be really wildly important to molecular biologists and to scientists. So just to step back briefly to say what is biofluorescence and how it relates into the ocean. We live in this like pan-spectral world. So we have the full Roy G. Biv up here on the surface. We've got our reds, our orange, our yellows. But this is not the case. As soon as you start descending in the ocean, as soon as you start descending down the ocean, you'll quickly start seeing that your reds are filtered out and even your violets are filtered out. And what you get as you go deeper and deeper here is this really pure blue spectral energy. So we use these filters in the lab. We spend about $1,000 for a little filter this big that will give you this clean of a spectra. And we use these now to get our images that I'll show you later. But this is the fish now that live in this world. They don't live in this beautiful like pan-spectral world that we see up here. They live in a primarily blue environment. It's just blue, blue, blue. So it's quite boring for them in terms of the ability to have other kinds of colors. So we'll think a little bit about what biofluorescence is doing to make their world a little bit richer. So just to kind of an idea of what like a non-fluorescent object. So I call this white light, and white light is like the light that's shining in my face right now because it's all colors of the rainbow. It's got everything in it, and you know that is if you took a filter like a blue filter and I put it over this light here, that I can get blue light out of this. It would be much dimmer than the white light that's coming out of that light there, but it would be blue. We'd see some blue light. So if I hit some blue light down onto a non-fluorescent object, it would just sort of absorb it, or it would maybe reflect some of your blue out. And a green filter wouldn't allow you to see it. So this is your eyeball trying to see this fluorescent light. So a non-fluorescent object would just keep the blue light to blue, the green filter would stop it from going out, a yellow filter, and your eyeball wouldn't detect anything. But if it was a fluorescent object, like relative to the jellyfish, like this anemone, if you take this white light, you filter it through the blue light now hits this fluorescent object, it's absorbing the blue light, it's converting that blue light to green, and now that green is going to make it through the filter here. So I don't want to see any of my own exciting blue light. I just want to see the light that's getting absorbed and re-emitted back out. And while this seems kind of practical or common, this is not a common phenomenon. On land-dwelling creatures, this is very rare. Like if I was to shine blue light on you, you guys wouldn't fluoresce. But when we're finding now that when we go beneath the ocean, when you live in this pure blue world, there are lots of animals that fluoresce down there. So my lab had been focusing primarily on coral reefs. And we had been isolating novel fluorescent proteins from corals, and we've been looking at the function of what fluorescence is doing in coral reefs for many years. We've taken several expeditions to Australia, and we've cloned about a quarter of the known fluorescent proteins from nature. We found all sorts of new sequences. We found the brightest fluorescent protein. We found some fluorescent proteins that do interesting physiological tasks. This one is a sensor for a process called phosphorylation. And we were pretty happy studying our corals. This has all changed quite recently too. And I was happy going down and trying to find out the conundrum of what are fluorescent proteins doing in coral reefs. I could see there's a diverse of them. There's reds, there's greens. They're making huge quantities of this stuff. This is something important. It turns out that some corals make like 17% of its soluble protein is fluorescent proteins. That's a lot of energy investing into this molecule. And if you look at some of these animals under white light, which they don't really ever get, they really only get blue light. But if you take it out of the water, out of the ocean, and you look at it under white light, or you shine a strobe on it, they could look pretty boring.